Welcome to iLecture Online, and here's another example of how to utilize Gauss's law to find the strength of an electric field near a charged object, in this case a spherical conductor that has a radius of 1 meter and a charge density of 2.5 microcoulombs per square meter, and the point of interest is 5 meters away from the sphere. So let's draw a picture of that. So here we have a spherical object with a uniform charge density. Since it's a conductor, you can imagine that all this charge will be equally distributed over the surface of the sphere. The radius of the sphere, so let's call this r sub s, is equal to 1.0 meters. Yes, 1.0 meters. And we want to know the electric field strength, E, and the direction at a distance of 5 meters away from the sphere. Now, we can imagine that the 5 meters assumes that it's from the center of the sphere. So this distance right here is then assumed to be 5.0 meters. And so what's the electric field strength that far away from this particular spherical conductor? All right, let's write that the surface charge density is equal to 2.5 microcoulombs per square meter. Now, if you didn't use Gauss's law, that would be a very difficult problem to try and calculate. But Gauss's law makes it a lot easier by assuming that he was correct in saying that the integral of the electric field strength at the surface of the Gaussian surface times the area of the Gaussian surface is equal to all the charge enclosed by the surface divided by epsilon sub naught, and epsilon sub naught is related to k via this particular equation here. All right, so we need a Gaussian surface to fully enclose this sphere here, and the best thing you can do is draw a spherical Gaussian surface of radius 5 meters all the way around, encapsulating this spherical conductor. So imagine a big beach ball 5 meters in radius that completely encapsulates this charge in such a way that you can then assume that the electric fields emanating away from this conductor will go through the Gaussian surface radially outward. And you can then also see that the strength of the electric field at this boundary of this Gaussian surface is the same everywhere along the boundary of the surface. Hence, the electric field at this location is the same as the electric field anywhere along the edge of that imagined surface. All right, and we can then say, using Gauss's equation, that the integral of E dot dA, it's a surface integral, is equal to the charge enclosed divided by epsilon sub naught. And again, the charge enclosed by the surface, of course, is equal to all the charge on this spherical conductor here. And we have to figure out what that is. Now, since the electric field is constant anywhere along the surface, the direction is, of course, different everywhere because it's radially outward from our conductor here. We do know that it's a constant magnitude. The magnitude doesn't change, so we can move the magnitude outside the integral sign, and that's equal to the surface integral of dA. Now, the surface integral of the area of the sphere is simply the area of the Gaussian sphere, and that equals, what am I doing here? I don't want an equal sign here, I want a multiplication sign there, and that should be equal to the Q enclosed divided by epsilon sub naught. So the beauty of this whole system here is that we draw a Gaussian surface in such a way that the electric field at the surface is a constant. We can simply pull it out of the integral sign. So now we need to know the area of a sphere, and of course the area of a sphere is 4 pi r squared. So we replace that. Let me go over here, have a little bit more room. So the strength of the electric field times the surface area of a sphere, which is 4 pi r squared, and we indicate the radius of the sphere. The radius of the sphere here is r sub s, and then the radius of the Gaussian surface, let's call it r sub g. So we mark this r sub g to indicate the difference between the radius of the conductor and the radius of the Gaussian sphere. So it's 4 pi r squared and r sub g squared, that's the area of the sphere, is equal to the charge inside. So how do we find out what the charge is on the cylinder, on the sphere? Well, we know the charge density, that's the charge per unit area, and then if we multiply that times the area of that sphere, we have the total charge. So we take the charge density sigma, and we multiply it times the area, which is 4 pi r squared as well. But remember, this is a different r. This is the r of the Gaussian surface. This is the r of the conductor. And so we'll write it sub s, because that's what we marked it here. And we divide that by epsilon sub naught. Notice that we have a 4 pi on each side, so the 4 pi cancels out. The r sub g and the r sub s are not the same, so they don't cancel out. And so now to isolate E, the strength of electric field, we're going to divide both sides by r sub g squared. So the strength of electric field is equal to sigma times r sub s squared divided by r sub g squared times epsilon sub naught. Now the epsilon sub naught can be replaced by 1 over 4 pi k. Since it's 1 over epsilon sub naught, we take the inverse of that, and we can write that this is equal to sigma times r sub s squared divided by r sub g squared times 4 pi k. And now we have an equation that allows us to find the strength of the electric field at the Gaussian surface. So let's go ahead and do that. So we can say that the strength of the electric field is equal to, we have sigma here, which was given, which is 2.5 times 10 to the minus 6 coulombs per square meter. That's the surface density. We multiply times the radius of the sphere, which we said was 1 meter. So that's 1 meter squared. We multiply that times 4 pi and k. So multiply this times 4 pi and multiply this times k, which is 9 times 10 to the 9th. That's newtons meters squared per coulomb squared. And take the whole thing and divide it by what's in the denominator, which in this case is the radius of the Gaussian surface squared, which we believe is 5 meters. Yeah, right there, 5 meters. So 5 meters quantity squared. And that will give us the strength of the electric field at a distance of 5 meters away from the charged spherical conductor. So let's calculate 2.5 e to the 6 minus times 4 times 1.9, that's pi. We multiply it times 9 exponent 9 and divide it by 25, which is the radius squared. And we get, rounded off, 11,300 newtons per coulomb. Now that is the strength of the electric field at the Gaussian surface, which was strategically placed at the distance that we wanted to know the electric field at, the strength of the electric field. And of course, it's radially outward in all directions. So we could say that E is equal to 11,300 newtons per coulomb in a radial direction outward. And this can indicate a three-dimensional radial direction. The strength of the electric field is 11,300 newtons per coulomb. Again, to summarize, to find the electric field strength at some distance away from an object containing charge like that, in this case it's a spherical object containing charge on its surface, to figure out what the electric field strength is at some distance, we draw an imaginary Gaussian surface around it. Since the object we had was a sphere, the Gaussian surface should be a sphere as well, so that the electric field emanating from the charged object will be radially outward and will be the same everywhere along the surface of that Gaussian surface. And by using Gauss's law, we can then multiply the electric field strength, which is a constant along the surface, times the area of the surface, which is equal to the charge enclosed by the surface, which is the total charge contained on this sphere, divided by epsilon sub naught. The rest, we just plug in the equation, plug in the numbers, and out comes the answer. So hopefully now with seeing several examples like this, the methodology begins to become clear and you'll be able to apply some of this yourself. So take another look at these and hopefully by now you're beginning to understand how to do these. Okay, good luck with these.